Good afternoon, students. In the last lecture, we have started the topic of inner transition elements, lanthanoids. There are some properties of lanthanoids completed in last lecture. Then the next topic from lanthanides, their electronic configuration. The topic electronic configuration of lanthanoids. Then see here, the valence general electronic configuration for the lanthanoids. These lanthanoids are also called the 4s series. Their valence electrons enter into the 4f orbital. That 4f orbital means the pre-penultimate shell of f orbital. There is the penultimate shell of d orbital also, and there is a last shell s orbital is also. From this you write the general valence electronic configuration for the lanthanoids. That is pre-penultimate shell of f orbital, you write n-2 f. Then n-1d, this is the penultimate shell of d orbital, and there is the last one ns. That ns contains the 2 electrons. Then d orbital, that contains 0 to 1 electrons. Then f orbital contains 0 to 14 electrons. That 0 means if that lanthanoid started from the lanthanum, that lanthanum contains the 0 electrons in f orbital, because actually the lanthanum placed in d block elements that contains the valence electron in d orbital, but their 4f orbital is 0, and that lanthanoids follow by the lanthanum. So in general you write n-2 f 0 to 14, n-1d 0 to 1, and last is ns2. Last is ns2. This is called the 4f series. That means there is a filling of electrons in 4f orbital. Then if n-2 is the 4, then n equal to 6, right? And lanthanides are placed in period number 6. So their last shell is the 6s, that is 6s2, then 5d 0 to 1, then 4f 0 to 14. This is the valence electronic configuration for lanthanoids. That lanthanoids started from the lanthanum. Okay? The lanthanoid started from the lanthanum. That lanthanum having the atomic number 57, right? 57. The electronic configuration of lanthanum is xenon 5d1 6s2. Xenon 5d1 6s2, or you write 4f0 5d1 6s2. There is no electrons in 4f orbital. There is a 1 electron present in 5d, so lanthanum belongs to the d block element. Right? Then see, lanthanum contains the xenon core for the 54 electrons. That means lanthanoids also contains the xenon core. So their general electronic configuration, you write xenon 4f 0 to 14, 5d 0 to 1, 6s2. 6s2. There is the filling of electrons from 4s 0 to 14 for all lanthanoids that contains the starting element lanthanum. That contains the starting element lanthanum. And xenon contains total 54 electrons. The electronic configuration of xenon is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, after 3d10, 4p6, then 5s2, after 5s2 there is the filling of 4d10, and last one is the 5p6. These are total 54 electrons. After xenon, there is the next electrons present in 4f orbital, 5d and 6s. This is the general electronic configuration for lanthanoids. See here, the energy of the energies of 5d orbital and 4f orbital that are very close. There is a very small energy difference between 4f and 5d. There is a one exception case for the lanthanum, that 4f orbital having the higher energy level as compared to the 5d. 4f orbital is slightly higher than the 5d orbital. So lanthanum showing the electronic configuration this: xenon 4f0, 5d1, 6s2. Instead of lanthanum, xenon 4f1, 5d0, 6s2. This is the wrong. This is the correct. Because 4f having the higher energy level as compared to 5d for the lanthanum. And after the lanthanum, there is the next element, cerium. In that cerium, the electrons enter into the 4f orbital. There is the filling of electrons in the 4f orbital. Right? Then, the electronic configuration of all lanthanides are here. There are total 14 elements included in the lanthanoids, and that followed by the lanthanum. So you write first electronic configuration of lanthanum. That is the elements lanthanum, then atomic number, then expected electronic configuration, and there is the observed. And there is the observed electronic configuration. There is the first element lanthanum. After lanthanum there is the cerium. Then next is the praseodymium. Next is neodymium. Next promethium. Next samarium. Their electronic atomic numbers 57, 58, 59, 60, 61, 62. After samarium, there is next europium 63. Next is gadolinium, that is 64. Then after gadolinium, next is the terbium. Terbium is denoted by Tb. Then dysprosium. Then holmium. Then erbium. Then thulium. Then ytterbium. And last is the lutetium. This lanthanoid series started from 57 to 71, including lanthanum. Then see, there is the first element, lanthanum. Okay, that lanthanum contains total 57 electrons. You write first expected electronic configuration of lanthanum, that is xenon core 4f0, 5d1, 6s2. 5d1, 6s2. Right? The next one is the cerium, that contains the 58 electrons. That having the electronic configuration xenon core 4f2, 6s2. There is no electrons in 5d for the cerium. Then after the cerium, there is the one electron included in the 4f orbital, and that show the expected electronic configuration 4f3, 6s2. Next, neodymium xenon 4f4, 6s2. Next, promethium xenon 4f5, 6s2. Then samarium xenon 4f6, 6s2. Then europium xenon 4f7, 6s2. Then gadolinium xenon 4f8, 6s2. Then next is the terbium 65, that show the electronic configuration xenon. 4f9 6s2. Next, dysprosium dy 66 electrons xenon. 4f10 6s2. Next, holmium 67 atomic number, that show the electronic configuration xenon. 4f11 6s2. Then next is the erbium 68 atomic number, electronic configuration xenon. 4f12 6s2. Then thulium, that thulium is 69 atomic number, electronic configuration xenon. 4f13 6s2. Then ytterbium, atomic number 70, electronic configuration xenon. 4f14 6s2. And last is the lutetium, that having atomic number 71, xenon. 4f14 5d1 6s2. 5d1 6s2. According to the expected electronic configuration from lanthanum to lutetium, only the lanthanum and lutetium that having the one electron in 5d orbital, that having only the one electron in 5d orbital. Then the observed electronic configuration for lanthanoids. There is some changes occurs in the observed, and that is here. There is the first one, lanthanum. Lanthanum showing the same as in observed, that is xenon. 4f0 5d1 6s2. 4f0 5d1 6s2. Next is the cerium. In this cerium, in observed, there is only the one electron in 4f orbital, that contains 4f1 5d1 6s2. 4f1 5d1 6s2. According to the expected, there is 2 electron in 4f, and that 4f and 5d energy levels are very close, so 1 electron shifted to the 5d. Then after the cerium, that xenon, praseodymium showing the same as the expected, xenon core 4f3 6s2. 4f3 6s2. Then next one is xenon 4f4 6s2. Then next is the same, that also showing the same, that also showing the same in observed. But there is the element gadolinium, that gadolinium having the 4f8 electrons and 6s2 in the expected. To achieve the extra stability, that 1 electron from 4f orbital goes to the 5d, and that show the observed electronic configuration xenon. 4f7 5d1 6s2. 5d1 6s2. Then after the gadolinium, that remaining all showing the same electronic configuration as the expected, that is xenon core 4f9 6s2. Then same. There is the last element, lutetium, also showing the same, that is xenon core 4f14. Then 5d1 6s2. 5d1 6s2. There is just 2-3 elements, they showing the difference in expected and the observed. according to the observed electronic configuration, that cerium, gadolinium and lutetium, they showing the one electron in 5d orbital. They showing the one electron in 5d orbital. See, this is the electronic configuration of lanthanoids. There is a two types of electronic configuration. First is expected and second is the observed. Let us see here. There is the two electrons present in 6s, common for the lanthanoids. Then lanthanoids have a tendency to show the +2 oxidation state. Right? This is the electronic configuration of lanthanoids. Then there is the next topic from the chapter, ionization enthalpy. Ionization enthalpy. Generally, these lanthanoids are placed in same period, that is period number 6, and according to the period, the periodic trend for the period, ionization enthalpy goes on increasing from left to right. The ionization enthalpy goes on increasing from left to right. Right? Their ionization enthalpy goes on increasing, but there is slight variation in the ionization enthalpies of lanthanoids. Why their ionization enthalpy increases? Because the coming electrons enter into the same shell, that is 4f orbital. Right? The coming electron experiences the higher nuclear attraction because of the poor shielding effect of 4f orbital. And due to the higher nuclear attraction for the valence electrons, lanthanoid showing the higher ionization enthalpy. Right? There is one question for the ionization enthalpy is given. Which of the following will have highest fourth ionization enthalpy? Which of the following have highest fourth ionization enthalpy? And there are some ions are given. There is the first ion, lanthanum 4+, second is gadolinium 4+, and last is lutetium 4+. They showing the same oxidation state, that is +4. There. How you find out which showing the higher ionization enthalpy? See here. There are the 2-3 points that affect the ionization enthalpy of ions. Right? First one, if there is a higher nuclear attraction, then higher amount of energy required to remove the loosely bounded electrons from the outermost shell. Then that element having the higher ionization enthalpy. But how you write the answer for this? First you write the electronic configuration of lanthanum, gadolinium and lutetium. That lanthanum is 57 and electronic configuration is xenon 4f0, 5d1, 6s2. Then next is the gadolinium, that having that having the atomic number that gadolinium having the atomic number 64. The electronic configuration is xenon 4, 4f7, 5d1, 6s2. And your last is the lutetium that having atomic number 71, electronic configuration xenon 4f14, 5d1, 6s2. 5d1, 6s2. Then see here, for these three elements, there is the 3 electrons present in a 5d and 6s2. That means first these 3 electrons are removed. After removing the 3 electrons, if you remove the 4th electrons, that lanthanum showing the electronic configuration, only the xenon 4, and xenon is the highly stable. Xenon is the highly stable. Then in the gadolinium, if there is a removal of 4th electron, and that from the xenon 4f7. This xenon 4f7 is the stable electronic configuration because that having the half-filled electronic configuration in f orbital. So that achieve the extra stability. If you remove the electron from 4f7, that require the higher amount of energy. Then, in lutetium, after the removal of 3 electrons from 5d and 6d, there is very large amount of energy required to remove electrons from 4f orbital because xenon 4f14 is highly stable electronic configuration that require the higher and higher amount of energy to remove electrons. That means all these 3 ions, they having the higher ionization enthalpies. That means all these 3 require the higher amount of energy to remove the electrons from outermost shell. But there is one sentence, the energy required to remove unpaired electron is less as compared to the paired electron. Clear? Ionization enthalpy for lanthanides. Then, after ionization enthalpy, there is the next property, oxidation state. The oxidation states of lanthanoids. Their general electronic configuration is xenon 4f 0 to 14, 5d 0 to 1, 6s2. There is total electrons present in 4f, 5d and 6s2. The common oxidation state for the lanthanoids is +3. The common oxidation states for the all lanthanoids is +3. In which, how they showing the +3? There is the removal of 2 electrons from 6s orbital and 1 electron from 4f or 5d orbital. There is the 2 electrons first from the 6s orbital and 1 electron from these 2 orbitals. That is from 4f orbital or 5d orbital. These 4f electrons are strongly screened by inner electrons of 5s and 5p electrons. Thus, 4f electrons are not involved in bonding. 4f electrons are not involved in bonding. Besides these oxidation states, beside +3 oxidation states, the lanthanoid showing +2 and +4 oxidation states. The lanthanoid showing +2 and +4 oxidation states. That +2 showing by the removal of 2 electrons from the 6s and +4 showing from the removal of electrons from 4s orbital. These lanthanoids form in case of F0, F7 and F14 electronic configuration. There are some resulting ions. For this electronic configuration are given, first is cerium 4+. Cerium exists in a +4 oxidation state with 0 electron in F orbital. With 0 electron in F orbital. Then europium in 2+ and terbium in 4+. They showing the electronic configuration of 7 electrons in F orbital. And there is the last one, ytterbium in +2 oxidation state, that having the 14 electrons in F orbital. That show the 14 electrons in F orbital. Clear? That means lanthanoid showing the common oxidation state +3. Besides this +3 oxidation state, they have a tendency to show the +2 and +4. Why they does not showing the higher oxidation states? Because 4f electrons are not involved in bonding. Clear? Then there is the next property for the lanthanoid, color and spectra. Color and spectra. We have already see this color property for the d block elements. The d block elements, that is transition elements, they form the colored compounds. Same here. F block elements, or you say lanthanoids, they also have a tendency to form the colored compounds. And the common oxidation states of lanthanoid is +3. They form the trivalent ion M+3. These M+3 ions of lanthanoid are colored in solid state as well as in solution. Right? Why they form the colored compounds? There is a 2-3 points behind the color. These elements have a tendency to absorb the radiations from visible region. This is the first. Then second, lanthanoids having the unpaired electron in 4f orbital. So there is the possibility of FF transition. Right? Due to this FF transition, they absorb the radiation from visible region and appear as a color. The color of these ions, the color of ions of lanthanoids having NF electrons is about the same as those having 14 minus n F electron. 14 minus n F electron. Here n is the integer from 1 to 30. Here n is the integer from 1 to 30. Then there are some ions are given here. There is the lanthanoid ion, number of electrons number of F electrons, color. There is a first pair, praseodymium in +3 and thulium in +3. They having the F electron for F2, for F12, for F2, for F12, and both having the same color, that is green, because they having the same electrons. See, for that there is the n equal to 2, n equal to 2, that means 14 minus 2 equal to 12 electrons, and here is already 12 electrons, 12 F electrons, that means show both having praseodymium in +3 and thulium in +3. They both having the same number of F electrons, so they appear as the same color green. So they appear as the same color green. Clear? The color of transition and inner transition elements due to the number of unpaired electrons present in their valence, that is in d and in F orbital. Clear? Then after the color and spectra, there is a next important property, atomic and ionic radii. Atomic and ionic radii of lanthanoids. We have already studied this property. Atomic and ionic radii. These lanthanoids are placed in period number 6. They are placed in same period, and according to the period, that atomic as well as the ionic radii goes on decreasing from left to right. The atomic and ionic radii of lanthanoids are gradually decreased from left to right, is called the lanthanoid contraction. It's called the lanthanoid contraction. There is a gradual decrease with the increase in atomic number. With the increase in atomic number from 57 to 71. There is a gradual decrease in atomic or ionic radii. Why there is a decrease in atomic and ionic radii? Because there is just one electron is added from lanthanum to the lutetium, that is from 57 to 71, and this coming electron is added into the 4f orbital. Coming electron added into the same shell, or you say the 4f orbital, right? And the valence electrons having the higher nuclear attraction because of the poor shielding effect of 4f orbital. There is a poor shielding effect of 4f orbital because f orbital having the diffuse shape, and due to this diffuse shape, that having the poor shielding effect, so the valence electrons experiences the higher nuclear attraction. So the valence shell is slightly pulled towards the nucleus, and that distance goes on decreasing from left to right. Yes? The atomic and ionic radii of lanthanoids decreases with increase in atomic number, called lanthanoid contraction. Because of the higher nuclear attraction. Clear? Here is the properties of lanthanoids are completed. There is remaining only the applications that are taken in next lecture.